Welcome to the next lecture on derivatives. In the last lecture, towards the end, we were looking at the derivatives of function defined in parametric form. So, today we will continue with some more examples of derivatives of function defined in parametric form, and then we will look at some other results. So, for example, let us look at equation of the parabola y square equal to 4ax can be written in the parametric form as x is equal to at square and y is equal to 2at. Right. If you put y equal to 2at, y square is 4a square t square, which is equal to 4a times at square. So, to find dy dx, so dx dt is equal to 2at and dy dt is equal to 2a. This implies therefore, dy dx is equal to dy dt, which is 2a divided by 2at, which is equal to 1 by t. Right. This is the derivative in terms of the parameter t. We could have also calculated directly here, if we differentiate with respect to x of y square is equal to d by dx of 4ax. This gives 2y times dy dx is equal to 4a, which implies dy dx is equal to 4a divided by 2y, it is equal to 2 times a by y. Putting y equal to 2at, putting y equal to putting y equal to 2at, in this we get dy dx is 2a divided by 2at, which is equal to 1 by t, which is same as this one. Let us look at one more example. Find dy dx if x is given by a times cosine theta plus theta sin theta and y is a times sin theta minus theta cos theta. So, here x and y are given in terms of the parameter theta. So, to find dy dx, we need to find the derivative with respect to theta. So, dy dx is equal to dy d theta by d theta dx d theta, which is equal to dy d theta is equal to a times, if you differentiate this, sin theta gives cos theta minus derivative of theta cos theta will give, by product rule, derivative of theta is 1. So, this gives cos theta minus theta times cos theta derivative is minus sin theta. So, this becomes plus theta sin theta, and the derivative of x with respect to theta gives a times minus sin theta plus sin theta plus theta cos theta. So, here cos theta cancels and sin theta cancels and a cancels. So, this is equal to just tan theta. Okay, so then the next thing is we can talk about higher order derivatives. So, suppose y is equal to f x is differentiable and the derivative f prime x is a differentiable function then we can find the derivative of f prime x, the derivative of f prime x is called the second derivative of f x, and we denote this and is denoted by f double prime of x, or if I write y equal to f of x. So, the derivative is denoted by d2y by dx square. So, the second derivative is the derivative of the first derivative, and similarly we can define higher order derivatives, that means the third, fourth derivatives. Also. So, for example, let y is equal to a times cosine x plus b times sin x, where a and b are constant. And so that if I take the second derivative of y with respect to x, this plus y gives 0. So, we need to find first the first derivative and then differentiate it again to get the second derivative. So, y is equal to a cos x plus b sin x. That means that dy dx is minus a sin x plus b cos x, and so the second derivative d2y dx square is equal to minus a cos x minus b sin x. Therefore, which is equal to simply minus of y. So, d2y dx square plus y is equal to 0. Now, let us talk about sign of derivatives. So, suppose f of x is an increasing function in an interval let us say I is equal to some open interval a b. So, what does this mean? So, that is if x 1 x 2 belongs to I and x 1 is less than x 2, then f of x 1 is less than or equal to f of x 2. So, this we call increasing function or non decreasing function. If whenever x 1 is less than x 2, then f of x 1 is less than or equal to f of x 2, and we say strictly increasing if we say f of x 1 is strictly less than f of x 2. Similarly, we can define decreasing function. So, here the graph of the function will be if I have this interval a to b. In this interval, the value of the function keeps on increasing as you go from a to b. Now, what can we say about the derivative? What can we say about f prime x if f x is a differentiable function? So, note that how is the derivative defined. So, we have f prime of x is nothing but limit of h approaching 0 of f of x plus h minus f of x divided by h. So, if we look at the right hand derivative, this is equal to the limit of h approaching 0 from the right of f of x plus h minus f of x by h. So, here if you see, because f is increasing function, this f of x plus h greater than or equal to f of x here, this is greater than f of x since f is increasing. So, the numerator here f of x plus h minus f of x, this is non negative and the denominator h is positive. So, therefore, the derivative is this must be greater than or equal to 0. If the limit exists, then this limit must be non negative. Similarly, if we look at the left hand derivative, this is the limit of h approaching 0 from the left of f of x plus h minus f of x divided by h. Now, here because h is negative, here both numerator and denominator are negative, Therefore, again left hand derivative is again greater than or equal to 0. So, what we have seen is that thus if f x is a differentiable function and is increasing on an interval I, then the derivative f prime x must be greater than equal to 0. Similarly, for a decreasing function which is differentiable, f prime x must be less than equal to 0, right. So, if it is increasing, then the derivative is greater than equal to 0, if it is decreasing, then the derivative is less than equal to 0. As an example, let us look at f x is equal to x square. So, if you draw the graph of this function, we get this parabola y equal to x square, and we can easily see that so this is f x is decreasing in the interval minus infinity to 0 and increasing in the interval zero to infinity, right. The function is decreasing for x negative, and for x positive the function is increasing. So, thus f prime x is less than or equal to 0 on minus infinity to 0, and this is greater than equal to 0 on 0 to infinity. Of course, here I can calculate the derivative here, and if I directly calculate the derivative f prime x is equal to 2 x, this if x is negative, this is less than 0 on minus infinity to 0, and this is greater than 0 on 0 infinity. So, this is an example to show that this function which is decreasing in some interval and increasing in some other interval, there the derivative sign is negative when it is decreasing and positive when it is increasing. Okay. Next thing I will discuss is about local minima and maxima of a function. So, suppose f x is a given function a point x naught is said to be a local minimum let me also define maximum or local maximum of f of x if there is an interval let me call a comma b containing x naught such that f of x naught is less than or equal to, for minimum this will be less than equal to f x, and for maximum this is greater for all x belonging to a b, and f x naught is greater than equal to f x for all x in a b for local maximum. So, let me explain this by a graph. Suppose we have this graph, if we see this point here x naught, this is a local minimum of this function, because if you see, if I take an interval here a b, then the value of the function f of x naught is the minimum of all the value of the function in this interval. But if I look at this one, so this is a local min, but this point and this point corresponding to this we have these points, this is local max, this again corresponds to local max, because if you see here I can take an interval like this, and then you see that this is the maximum value. So, here f of x naught is the minimum value in some interval containing x naught, and for local maximum f of x naught is the maximum value of f of x in some interval. So, if we look at this graph for f x equal to x square, if I look at x naught equal to 0, this is a local minimum. This is because here from the graph you can see that this value at 0 gives me the minimum value in any interval containing 0. So, therefore, this is local. Here it is also the global minimum, because this is the minimum value of the function. But how do we determine this local minimum or maximum using the derivative? So, here if we see local minimum, that means what? The value of the function to the left of this must be greater than this value, and the value of the function to the right must also be greater than. That means that the function must be decreasing in the interval to the left of this x naught, and it must be increasing in the function in the interval to the right of this point x naught. So, x naught is a local minimum if f x is decreasing in an interval to the left of x naught and is increasing in an interval to the right of x naught. Similarly, for local maximum it will be the other way. For local maximum, the function is increasing to the left of x naught and decreasing to the right of x naught. And now this we can express in terms of the derivative. We have the first derivative test to determine local min or local max of any differentiable function f of x. What is this test? So, if we have this x naught and to the left of x naught we want for local minimum this should be decreasing. So, this we denote like this is decreasing here and increasing to the right of x naught, then this is local min, and for local max we must have the function is increasing and to the left and decreasing to the right. Now, if we look at the sign of f prime x, for local min the function is decreasing to the left of x naught, that means that the sign of f prime x is negative to the left of x naught and positive to the right of x naught, and for local max this is the other way, it is positive to the left of x naught and negative to the right of x naught. So, the first derivative test says that if the function is differentiable and if the sign of the derivative changes from negative to positive around x naught, then we get local min, and if it changes from positive to negative, then this must be a local max. So, let us look at some example. Let us look at f x equal to x square minus 3x plus 2. So, this function, if I find the derivative f prime x, this is equal to 2x minus 3. Now, we want to look at this sign of this f prime x. So, f prime x, you can see that 2x minus 3, this is equal to 0 at x equal to 3 by 2, and this is negative if x is less than 3 by 2, this is positive if x is greater than 3 by 2. So, we get this point 3 by 2, and for x less than 3 by 2 the derivative is negative, and for x greater than 3 by 2 the derivative is positive. That means that the function must be decreasing here and increasing to the right of 3 by 2. This means that, so therefore, by the first derivative test, f x has a local minimum at x equal to 3 by 2. In fact, here I can write this f x as, this is x square minus 2 times 3 by 2 x plus 3 by 2 square, and then plus 2 minus 3 by 2 square. So, this is equal to x minus 3 by 2 whole squared, and then I have 2 minus 9 by 4. So, that gives me minus 1 by 4. So, we see that this x minus 3 by 2 square, this has to be always greater than equal to 0. So, this f x has to be greater than equal to minus 1 by 4, and if I put x equal to 3 by 2, then f x is exactly equal to minus 1 by 4. So, f of 3 by 2 is equal to minus 1 by 4. Therefore, f x takes the minimum value at x equal to 3 by 2, and this is the minimum. Here if you draw the graph, this f x is equal to x minus 3 by 2 square minus 1 by 4. So, at x equal to 3 by 2, this takes the value minus 1 by 4, and you can plot this. This is a parabola. The minimum value is at 3 by 2, and if you put x equal to 0, this gives me 2. So, we get a parabola like this, and this 3 by 2 is the local minimum as well as global minimum in this case. Okay. I will state one important theorem. This says that any continuous function f of x on a closed interval let us say closed interval a b attains its minimum as well as maximum value on AB. So, what this is saying is that if we have any closed interval AB and the function is continuous, then there exists, that is for continuous f of x on closed interval AB, there exists some x1 and x2 in this AB such that f of x1 is always less than equal to f of x and f of x is less than equal to f of x2 for all x belonging to AB. So, we will not look at the proof, of this theorem, but note that the assumptions are necessary. So, there are two crucial assumptions in this theorem. One is that this function is continuous and another is that the interval is closed interval. So, first one, it is very easy to see that if the function is not continuous, so continuity is necessary. Because otherwise you can have, say, this is the function and suppose I take and at this point this is equal to 0. So, the function is defined on the closed interval 0 1. So, this is f x is equal to x for 0 less than equal to x less than half, and this is equal to 0 at x equal to half, and then this is 1 minus x if x is bigger than half and less than equal to 1. This function, you can see that this is discontinuous at half. Now, if you look at this function, this does not attain its maximum value. So, no maximum value. Another thing is that closed interval is again necessary. The result is false for open interval. For example, consider f x equal to 1 by x on the open interval 0 1. So, the function is 1 by x. Note that this function, as x goes to 0, this goes to positive infinity. So, again this function f x has no maximum value on the open interval 0 1, even though it is continuous. So, we require both the continuity as well as the interval being closed for this theorem to be true. So, after this, the next we will learn the two other very important theorems on derivatives, which are the Rolle's theorem and the mean value theorem. So, let me first state the Rolle's theorem. So, this says that suppose f x is a function defined on a b satisfying the following three conditions. First one is that we require f of x to be continuous on the closed interval a b this is on closed interval a b. Second is f x is assumed to be differentiable on open interval a b, and the third condition is that the value of the function at the end points f a is equal to f of b. Then the conclusion is that then there exists at least one point C belonging to the open interval a b such that f prime of C is equal to 0. So, let me try to explain this theorem by showing a picture. So, let me explain this Rolle's theorem by means of these examples. So, I have this interval a b, and what we have, the third condition says that f of a must be equal to f of b, and the function is continuous in this interval and differentiable in the open interval. So, it might be that we have a function like this, or it can be I have f a and f b, so if you see what the conclusion says that there exists at least one point C where the derivative is equal to 0, and we know that the derivative equal to 0 means that the slope of the tangent line is parallel to the x axis. So, here if you see this point, the tangent line is parallel to x axis here also. So, there are two values here where the derivative is 0. Here again we have a value c here where the derivative is 0. So, what this theorem says is that no matter what the function is, if it satisfies these three conditions, that it must be continuous in the closed interval a b, differentiable on the open interval, and f of a is equal to f of b, then we must have that at some point in between a b the derivative must be 0. Okay, so, this Rolle's theorem we will again try to see that these conditions that are specified here, these are necessary conditions. So, we will not look at the proof right now, but we will show that the conditions are necessary. So, first one that we said that the function must be continuous on the closed interval. Suppose we have this example, I have a function like this, and then I define, let us say this is 1 and 4, and I define the value of this function is equal to this. So, this function is f x equal to 4 if x is 1, and this is equal to x if 1 is less than x less than equal to 4. So, this function if you see, this f x is not continuous at x equal to 1, but other than that the function is continuous everywhere other than x equal to 1. F x is continuous everywhere else also. This function f x is differentiable on the open interval 1 4, and f of 1 is equal to f of 4. But if you see this function, there is no point where the derivative is equal to 0. There is no point in the open interval 1 to 4, but f prime x, because f x is equal to x in the open interval 1 to 4, f prime x is equal to 1 for all x belonging to 1 to 4. Thus, there is no c in 1 4 for which f prime c is equal to 0. However, this example does not contradict the Rolle's theorem because f x is not continuous on the closed interval one to 4. All right. So, I will stop here today. In the next lecture, I will show that the other two assumptions, the second assumption on the differentiability of the function in the open interval a b and the third assumption that f of a equal to f of b are also necessary for the conclusion of the Rolle's theorem, and then we will discuss the mean value theorem and then some applications of these theorems. Thank you.